I'm Sophie. Thanks for coming. I'm really excited to talk about federated learning. It seems like it's the future, so get pumped. Alright, so quick overview of what I'm doing. I'm going to do a brief introduction on machine learning, so at least we have the same basic knowledge before we talk about it. What's currently being used today to train AI models, why federated learning is better, and where it's being applied, and then a quick conclusion. So, should be fun. Alright, so starting off, this is what Herbert Simon has to say about what learning is. It's any process by which a system improves performance through experience. So, I mean, if you're a student, you're going to do better on a test if you've done the homework. If you're a runner, you're going to do better on a race if you went to running practice. Same with computers and AI models. If you give the computer more data to practice on, the model is going to be more accurate and have better predictions. This is similar to that. So machine learning, in essence, is the study of algorithms that improve their performance at some task with experience E. I think that's basically what I said. Performance and experience are still there, and then task is what you're applying it to. So, to give perspective, I'm guessing most of you are computer science, probably. So in most of the intro classes, you're doing traditional programming, where you give data and a program into the computer, and you get an output. So if you want to build a program that finds all the even numbers, you'd give data would be, say, your list of natural numbers, your program, you do some modulo function to get 0. You put it into the computer, you get an output of all the even natural numbers. Machine learning differs in that the inputs are now data and your expected output, and the computer gives you the program. And this differs from traditional programming because now your data set has to be a lot larger in order to get the right model or program out. At least if you want a good model. You can get a bad model. Starting with kind of an easy example, given these numbers, you can recognize what the numbers are, but it's hard to contextualize what makes 2 a 2. So this is an example of where machine learning can come into play. You give a data set, you identify which ones are good, and it can learn to identify in more scenarios. Again, here are some applications of how ML is used. I think the easiest case is finding, fitting data to functions. You've probably done that in middle school science where you do line of best fit. This is from my 321 security class, and you're just graphing the length of time it takes to find a collision based off the size of a password. As you can tell, it goes up, and you can use this line of best fit to predict how long it would take to find a collision for a 256-bit password. Besides fitting data to functions, ML can be used to classify data. 2 summers ago, I did a drone project where I went to the mountains and worked on flower phenology research, which is the life cycle of flowers. The idea was, if you take a drone and fly it over the site, it captures images of the land. Is there a way that you can put those images into a computer, run an AI model on it, and have the model tell you what flowers are there, and if they're in bloom, in seed, in bud. In order to train that model to do this, you needed to provide it data. And so going out to the field, you could look at a flower for that site. You can tell what color it is, what else, the date of it. So, it's going to stay pretty consistent season to season, year to year. So when it blooms, that's important. the location itself, we did 23 sites. Just general information to train it, and you import that into the system. I think, yeah, overall, just more data helps the model train. I think just general considerations for machine learning overall. There can be data bias. If you take in like the ethics and tech class, you learn about data bias. There was a documentary on facial recognition and how the model was trained on white men, and so when a black woman tried to use it, it didn't recognize her as human. This is really problematic when these systems are being used in airports or like concerts, because there's half your population, depending on where you are. In addition, poison data training is worth mentioning. If someone, like a bad actor, puts in bad data, how does that influence your model? System hijacking, if someone takes your model, what can they do with it? I mean, in conclusion, how much are we trusting this model? How much do we want to know about how the model works? Or is it just a black box? Those are just general considerations for AI models. So, that's the background. Getting into this presentation, there seem to be two main ways to train an AI model. First way is the centralized model, and I'll talk about that first. That's what's being used right now for the most part. It's kind of the classic model. The second model that I'll be discussing is Federated Learning, and that is a decentralized model and provides layers of privacy, which should become the future. There was also edge machine learning, which is kind of a third option and is a blend between the two. If you're curious, you can look into it. So, centralized model. The general basis of how this works is you have your devices with data. So you have plenty of devices every day that you interact with. Your phone, your laptop, car, just anything that provides data if you have a smartwatch. And the idea is you send your data to a central server. And on the server, that's where the machine learning goes into play, and you train the model on that. And the server outputs an AM model. It's great because all your data is right there. You can easily understand how the model works to an extent just because you have the data with you. And I mean, that's why it's used now. It's the easiest and it's quick. I think the other example I liked that was easy to make sense of it was the bus example. If you have a bus, you can stream the data into the server. So when it breaks down, who's driving, the mileage, just general statistics. You can have the server do AI and produce a model. And the model can then be used to make generalizations. So that can be used to predict how the bus will do in different conditions, such as if it's really hot or really cold. So it's a powerful tool. It doesn't offer communication or privacy, which I'll get into later, but there just are general problems. Privacy is the main one. If you have all this data and you're giving it to the server, now you don't have your data anymore. Well, you do, but so does the server. So if bad actors take the server or have control of the server, they can access your data. In fields like finance and, I don't know, health, that's really problematic, and they do not give out their data. It's expensive for a reason. So that's not great. How can we solve this? One idea is, what if instead of putting all the data onto the server and having it train and outputting a model, what if you put the model on each individual device and have the model train locally and have the device then output the new model back? In this scenario, your data would never leave your device and the model would reflect the new data, but again, you still have control over your own individual data. This exists. It's great. It's called Federated Learning, and that's why we're here today. It's relatively new. There's news articles every day about it and how it's being used. It was originally coined by Google in 2016, and I think they were just trying to do software updates on their phones and protect privacy. So it is used, it's relatively new, and it's going to keep growing, I think, as the field expands. How does it work? I briefly mentioned this. Again, with this example, you have your initial AI model, and now you're distributing it to the individual devices to be trained locally. From there, the devices send back the new model that reflects their data, but varies. Then you aggregate the models together, and you get your global model or your new version of the model, and that can be distributed to other cases and devices. With the bus model, now it's being trained on each bus, and what can I say about this? It's just a lot better because we have generalization still, but communication is a huge one, because now the bus doesn't have to transmit the data to the server, and that is great because communicating all this data is a lot of overhead for a device. And so if you're training it locally, it only has to run the computation, change the parameters, and then return the new model. So that is very efficient. I mean, privacy, again, it's running locally. These are the two main models I found for how it's being done. The ones I just went over were kind of the aggregation model, where you have your server, you send it to the local training nodes, and then they send it back and it's aggregated. You can do it different ways. One was peer-to-peer. I don't know if we've had our peer-to-peer talk yet, but it's similar where the different nodes are just sending their output to the other ones, and they're just training on each other. And then that's how it just gets aggregated together. There's a third one, which is sequential, which is just in a line. Again, pretty basic. For the aggregation server, at least, you don't necessarily have to combine all the models equally. You could have one model that's more influential than others, and I think that's important. So if you trust one source more than the other, then you can reflect that. Yeah, so weights, client batch size, that kind of thing. So, where is this applied? I have 3 applications for you. The first one is Google. They have a keyboard predictor. I'm sure if you have an iPhone or any device, you've seen like keyboard prediction, and it's unique to you, where if you like text in certain slang, it can pick up on that. So Google's keyboard predictor is similar. It has 600 languages. It's reading everyone's different ways of texting and giving them different predictions. The idea is, how are they training the model? Because it takes a lot of data, but obviously you don't want to give all your texting data. The idea is the model goes on your phone, it trains, and it sends back the new model. They use Fed averaging, which is federated averaging, which is somewhat weighted, but that's not super important in this. It's just how they average it together. That's cool. Also, autonomous vehicles. It's used in that, similar to the bus example, where there's a ton of data. I read that for Teslas, they generate 1 gigabyte of data every second, which is a ton. And obviously, like, there's where you see the overhead of it's impractical to constantly stream the data to the server, and that's why putting the model on your own car saves money. So reduces overhead and is clearly superior to centralized learning. I think the third application is the most applicable, and it has to do with healthcare. In the health industry, there's like HIPAA and other privacy issues, which is problematic because how do you do research if you can't share data? The Rhino Health database is it sounded like the leader in using AI for healthcare, and they are implementing federated learning. They partner with a lot of researchers and institutions, so the individuals can upload their data or like train with their data and then return the model, and then in return have access to the global model that's been uploaded with tons of data. That's great. I read that one case of it being used is with a pancreas cancer research. It involves 11 different institutions, like one is Johns Hopkins, so definitely somewhat reliable partners. And the idea is they have access to the original model and they can train it on their own data and then return the model. But because there's 11 different institutions, there's a wider range of patients, backgrounds, ethnical demographics, and whatnot. And I mean, as a whole, having AI to help guide medical research unlocks a lot of different abilities. So it's definitely very useful and should be used. Unfortunately, there are some problems which make it hesitant to be used. I think the first is trust among the partners and data poisoning. In the previous example, if you have 11 institutions that are contributing to your global model, you have to be able to trust all 11 institutions that they're not ruining the model with bad data. We live in a capitalistic society, so it's hard to have everyone have the incentive to want to help each other. So that's a real problem and should be proceeded with caution. I read that they are having a different idea where you can kind of use blockchain and federated learning together, and blockchain provides an incentive to do the right thing. That could be an option to solve that, but we'll see. There's also leakage via reverse engineering. I read that, I don't know, I think it's pretty straightforward. You can reverse engineer things. It's kind of hard, but if you know what you're doing and if there's a huge enough payoff to do it, you could figure it out. In addition, timing updates. Since the models are all trained on different devices and they have different models, there could be issues when you combine them. I think it could be solved. I feel like the internet agrees with me, but it's worth mentioning. Model interpretability, that is a lot with machine learning as a whole. If you've used ChatGPT, which I'm guessing or hoping you at least heard of it or tried it out, it's very much a black box. You can't necessarily trust what's going on because you don't know what it's doing to get the output. You just kind of have to take what it gives you with a seed of caution, hopefully. And that's the issue with this, where you don't have access to all the data that creates the model. You only have what maybe you contributed to it, and that kind of can harm your ability to interpret the model and better understand what's going on. And you just have to trust that it's the right answer. What else? The model size. This could be an issue depending on your device. Allegedly, if the model's super big, it can't fit on your device, which could be problematic. However, I don't think that's a huge problem because Argos is one model that I looked at, and it does language translation. It only takes 100 megabytes, which you can run on most modern day devices, Deepface is another one that recognizes emotions. It only takes 500 kilobytes. ChatGPT, I couldn't necessarily figure out, but it sounded like ChatGPT, they have, 175 billion parameters, and Deepface has 120 million, which is like 10 times-ish. So 10 times 500 kilobytes is still not that big in general. So it seems reasonable. I don't think that's a problem. The other problem, the last one, does seem like an issue. Models can memorize information, which is kind of bad if you're trying to protect data. Especially with medical data, if you have information that's very unique, if you have like a unique patient, some models will kind of retain that and be like, oh, this is different, and hold on to it, which is really bad because now your data is not as anonymous, and that can lead to issues. I did find a solution to that. Federated learning is better because it trains on an individual patient. So if you are weird as a patient, it's a little less of a flag compared to other patients because it's all your data. And so theoretically, it wouldn't flag it as much. And then once it's aggregated with the rest, it should be less memorized. That's a little iffy, gray area, but we persevere. Okay. This I just thought was interesting for manipulating the model. That goes hand in hand with data poisoning. If you can influence the model to memorize information, that's kind of poor. This was one attack that I could find. I was trying to find a real attack. It was difficult. It's called a gradient ascent style attack. And the idea is you can somewhat manipulate the image to have the output you want. This could be applicable to federated learning in the sense that you could sway it to memorize information. I don't super understand it. I don't think anyone super explored it, but you could be the first. That's the conclusion. If you want to learn more, I found that there's a bunch of open source libraries that offer federated learning. TensorFlow and Flower seem like the most widely known, and they're open source. I watched a video. Didn't seem that hard to implement. I didn't watch the whole video though. There's also some classes that you could take if you're interested. 325 is privacy, which has a whole unit on this. 369 is distributed computing, which, I mean, this is kind of distributed computing. And then 570 is machine learning. Very interesting. This article I skimmed if you're interested about blockchains and how it can be used with federated learning. That's an option. There's 3 barcodes. This one, I think you could just learn about how unique your internet presence is. In retrospect, that's not very relevant, but it was really cool. The middle one is a comic on federated learning. It's worth a read if you want time. And then the first one, it's through Google and it has research and it's very interactive. We can look at it later, but those are all 3 interesting resources. Yeah. Thank you.